Hey everyone. So this video you don't have to watch, only if you want to hear me talk through the notes instead of you just reading stuff and writing things down. Chapter 5, we're going to start talking about antiderivatives. As the name implies, instead of finding the derivative of a function, we're going to be trying to think of a function whose derivative is the thing that we have. So we are going to start with our function 2x, and we think to ourselves, what function has a derivative that is 2x? That is x squared, because x squared, when we take the derivative, we move the exponent down to the front, we subtract 1, and we get 2x. So what we're going to be doing a lot this chapter is using our derivative rules backwards. But here is something we have to think about. Are there other functions whose derivative is 2x? How about, for instance, x squared plus 2? When we take the derivative of that, we still get 2x. Or maybe we have x squared plus 5. When we take the derivative of that, that is also 2x. So there's something we have to take into consideration with these antiderivatives. When we go the opposite direction of taking the derivative, our antiderivative, we have to worry about these constants. So, if f, capital F, is an antiderivative of f, lowercase f, on the interval I, then g is the antiderivative of f on the interval if and only if g of x equals capital F of x plus c. The antiderivative plus c, which is a constant. We call it the constant of integration. So, the antiderivative plus some constant value. Sometimes we will know it, sometimes we won't. The family of functions g, so we're considering g to be all of these, which there are infinitely many, is the general antiderivative of f, the general antiderivative. So g of x is going to be, again, one more time, f of x plus c, capital F of x plus c, and this is a general solution to a differential equation. And a differential equation is an equation with derivatives in it. We will be solving some differential equations this year, and depending on how much math you do, if you're like into engineering or anything like that, you will be most likely having to take a differential equations class, which is solving equations that have derivatives in them. Excuse me. So if capital G prime of x is 2x, well then our capital G of x, that's our x squared plus c. Our family of functions whose derivative is 2x. So find a general solution to the differential equation below. If y prime is equal to 4, we take its antiderivative on both sides. The antiderivative of y prime is y. The antiderivative of 4 is 4x. And then we need our constant. I guess I should say that we're taking our derivatives and antiderivatives with respect to x. So how do we solve f prime of x equals 3x squared? Well, we take the antiderivative. The antiderivative of f prime is f of x. And what function has a derivative that is 3x squared? Well, the exponent has to go up. The number in front deals with that exponent. I think we're getting x cubed plus c. Because when we take the derivative of x cubed, we get 3 down in front, x squared plus, and the derivative of constant is 0. And then our antiderivative of e to the x, well, that's an easy one. It's always just e to the x because its derivative is e to the x. We can't forget our constant. So, another name which I will almost always be using, I don't like to say antidifferentiation, not that there's a problem with it, but I just don't say it very often. Well, I'll be talking about things in terms of integration, which will either be indefinite or definite. Today we're talking about indefinite. So antidifferentiation, we're going to use this symbol right here, which is our integration symbol. It takes a little practice to get real good at writing it, but you don't have to be perfect at it. Let's break down some pieces of what this looks like. the thing that you're taking the integral of is the integrand. This dx right here, the x specifically, is the variable that you are integrating with respect to. So you can take an integral of different variables just like we can with derivatives. Capital F of x is our antiderivative. And c again is our constant of integration. So, with this idea in mind, the integral of capital F prime of x dx is capital F of x plus c. Integration and differentiation are inverse operations. They undo each other. Okay, moving right along. Some basic integration rules. What is the derivative of 0 dx? We think to ourselves, what kind of functions give us a derivative of 0? And that is all constants. And we don't have to do constant plus c, because if you take a constant plus another constant, it's just a constant. So we're just going to write c. Our integral of some constant k, so k is not a number, that is a constant right there. We have to think what has a derivative of just a constant number that isn't 0. Well, that is a linear thing. So our antiderivative is k times x, and then we can't forget our plus c, our constant of integration. You cannot forget your plus c when doing indefinite integrals. Something else to point out about a constant, a coefficient in front of things when you're taking integration, you are able to move that constant out in front of the integral. So the integral of k times f of x dx is the same thing as k times the integral of f of x dx, which we'll write as capital F of x plus c. Don't forget your plus c when doing indefinite integrals. If you're taking the integral of two functions being added or subtracted, as maybe you might guess, that is the same thing as doing the integral of f of x dx plus or minus the integral of g of x dx. So you can split up integration when it is just pluses and minuses. Same thing that we did for derivatives. Remember, with derivatives, if it was multiplication or division, we had different rules for that, and we have to be careful with multiplication and division. For integrals, we can't just take the integral of pieces, but when it's just plus and minus, when it's just adding and subtracting, we can split it apart. Our general power rule, this is how you can think of this if you need kind of a rule, and it's kind of hard to think about these because sometimes the numbers make it a little challenging. The general power rule for integration is you take 1 over n plus 1 times x to the power n plus 1 plus c. So you add 1 to the exponent, but you know that when you were to take the derivative of this, that you would move an n plus 1 down to the front. So to make sure that it's not there, you need this 1 over n plus 1. Don't forget your constant of integration. Trying to think about our derivatives backwards. The integral of sine is negative cosine, because the derivative of negative cosine, I don't know why I just wrote dx. The derivative of negative cosine is sine. Don't forget your plus c. Whose derivative is cosine? So the integral of cosine is sine of x plus c. Whose derivative is secant squared of x? That would be tangent. Don't forget your plus c. Whose derivative is e to the x? Well, that is, oops, that kind of looked gross, is e to the x. Whose derivative is 1 over x? That is the natural log. And be careful here. I'm going to write something that needs a little bit more thought as to why. I'm going to put absolute values around the x. Why do I need to do that? Well, let's think about the function 1 over x. its domain is x is just not allowed to be equal to 0. So when we take the integral, we need a function whose domain is the same, just not allowing to be equal to 0. If we didn't have these absolute values, we wouldn't be allowed to plug in negative numbers, but we want to be able to do that. So we have to be very careful. Watch your absolute values with this. When you take the integral of 1 over x dx, it's the natural log of the absolute value of stuff. Now, of course, with the function on the inside, eventually will only be positive stuff. We won't have to write them. But for now, it might be a handy thing to just simply write the absolute values around the x. Going back up, whose derivative is secant tangent? That would be secant, so the integral of secant x tangent x dx, that is secant of x. Oops, that doesn't look like a plus, does it? Plus c. Whose derivative is cosecant x, cotangent x? Well, that would be negative. Ooh, what did I just do? Oh, it looks like I zoomed in. That was weird. Looks like our derivative is negative cosecant x plus c. We have this negative because remember when we take the derivative of cosecant, we get negative cosecant cotangent. So you got to make sure your signs all line up. Whose derivative is whose derivative is cosecant squared? That is negative cotangent. And finally, our last rule for now, we'll have plenty of rules just like we did for derivatives. Whose derivative is a to the x? Well, normally that's just a to the x, but if you recall, d dx of a to the x power, that's ln of a times a to the x. So we don't have this ln of a there. What would make that cancel when taking the derivative? We need a 1 over ln of a as our constant being multiplied by a of x. And I almost forgot my plus c. I'm about to start losing points if I forget that plus c. All right, so some examples to wrap up today. This is what your homework is going to be asking you to do, is taking antiderivatives or indefinite integrals. Don't forget your plus c when you're doing your homework. I need to think about whose derivative is each of these three pieces. So for something x squared, I know that we're going to go up a power to x to the third. When I take the derivative of that, that moves a 3 down to the front, which isn't there. So the easiest way to do this is just to divide by that power. So since we had a 5 in front, I'm going to put that 5 over 3, and you can double check that when you take the derivative of that, you get 5x squared. Minus, what's the derivative of x? What's the antiderivative of x? That's going to go up to x squared. And you can just take your coefficient and divide by that new power, which is 2. So we can simplify that. And what's the derivative of a constant? That's a linear term, 2x. And don't forget your plus c. So just simplifying one of those terms, we get 5/3 x cubed minus 2x squared plus 2x plus c. We don't have a nice way to do this next integral as is. So, just like when we first started learning derivatives, if you can simplify, please simplify. We're going to divide both those top terms by the square root of x. It gives us x to the power 3/2 plus 3 times x to the power 1/2 dx. And you might see me forget to do this all the time. I should put parentheses around there just to show you're taking the integral of all that stuff. You'll see me be a little sloppy about that sometimes. You try to be better than me. All right, when we look at x to the 3/2, when we go up for our exponents, that's going to go up to 5/2, and then we're going to have a 1 over 5/2, which we can simplify. Out front for our constant, we have our plus, and then x to the 1/2 power, we're going to go up a power to x to the 3/2, and we need to take our 3 and divide by that exponent, and we can't forget our plus c. Simplifying all that stuff, we get 2/5 x to the 5/2, and then 3 divided by 3/2, we flip that fraction in the bottom over. 3 times 2/3 is 2x to the 3/2 plus c. Two more quick ones. We can think about this other integral as 4 times the integral of 1 over x dx, which is 4 natural log absolute value of x plus c. And then